So in this lecture, I will discuss product measures. So I'm starting from some measure space. So I have omega j, then sigma algebra fj, and some measures mu j. Let's say for the moment that I have two of them, and I want to consider the product space, which is omega 1 times omega 2. So this is the set of points x, y, so all the pairs in which the first coordinate belongs to omega 1 and the second coordinate belongs to omega 2. And on this new space that I will call omega, I want to define a sigma algebra which will contain what I will call rectangle, which I will define in a second. And in this sigma algebra generated by the rectangles, I would like to define a measure starting from these measures mu1 and mu2. So let me explain exactly what is the goal. So let's consider a set Ej in the sigma algebra Fj. Let's represent by E1 times E2. So this is the product of E1 with E2, which are exactly as I defined omega 1, omega 2, the set of all the pairs xy such that x belongs to E1 and y belongs to E2. So this is a family of sets. These sets, E1 times E2, where E1 belongs to F1 and E2 belongs to F2, will be called rectangles. So I'm calling all such sets rectangles. Then I will denote by F1 times F2 the class of rectangles. So these are all the set of all rectangles. And if I consider one rectangle of this type, E1 times E2, I would like to define the measure of E1 times E2. So what is the natural definition for the measure of E1 times E2? I think you will agree that this is mu1 of E1 times mu2 of E2. So the goal will be to start from these rectangles, to define a function mu on the rectangles through that formula, and to extend this measure to this function to the sigma algebra generated by the rectangles using Kara-Theodori theorem. So I hope it's clear. We start with this class of sets, which I'm calling rectangles. I'm defining a function on this class of sets by this formula. And now I would like to extend this function to the sigma algebra generated by the rectangles using Kara-Theodori theorem. And so if you remember Kara-Theodori theorem, we first define a function on a semi-algebra of sets. Then we showed that this function, it's a sigma additive, and we apply Kara-Theodori theorem in order to extend this function, this measure, to the sigma algebra generated by the semi-algebra if the space is sigma finite. So so let's do that. So let me define precisely, so what are the rectangles? So rectangles, and as I said, I will represent the set of rectangles by the symbol F1 times F2. These are all sets which can be written E1 times E2. So these are all sets written in this form such that E1 belongs to F1 and E2 belongs to F2. So this is what I'm calling the rectangles, and the first observation is that the rectangles is a semi-algebra. So this is our starting point. This class of sets will be our starting point. And so let me show that indeed this class forms a semi-algebra. So remember, we have to prove two properties. The first one is that the set omega, which is omega 1 times omega 2, belongs to F1 times F2. But this is clear because since F1 it's a sigma algebra, it contains omega 1, F2 it's a sigma algebra, it contains omega 2. Therefore, omega 1 times omega 2, it's a rectangle, and therefore belongs to F1 times F2. Then I have to prove the second property of the semi-algebra, which is, well, assume that A is a set in F1 times F2, and I have to show that the complement of A can be written as a finite union of rectangles. So I have to show that there exists n, a finite n, and sets Aj such that A can be written as the disjoint union of the sets Aj. So for Aj in F1 times F2. Okay, so these are the two properties of the semi-algebra. So let's prove property B. Let's take an element A in F1, F2. All elements of F1, F2 are sets of the form E1 times E2. So I know that A is equal to E1 times E2. And maybe let me draw a picture to explain what we are doing. So here is set omega 1. Here is the set omega 2, say. I'm taking a set E1, a subset E1 of omega 1 which belongs to F1. So let me represent this set by this interval. And the same thing here. So E1 times E2 will be this set here. So here's E1 times E2. And now I'm taking the complement of E1 times E2. And what I claim is that the complement of E1 times E2, so A complement, well, I want to take all points which do not belong to this square. So what I claim is either the first coordinate belongs to E1, but then the second coordinate should be outside E2. So this is a first piece. So let me write it as E1 times E2 complement, which is the first piece which I represented here. Then I can also, it can be that the second coordinate belongs to omega 2, but then the first coordinate cannot belong to E1. So here's the set I'm now considering, which is E1 complement times E2. Well, and finally, maybe the first coordinate doesn't belong to E1 and the second coordinate does not belong to E2. And now, so this is a third set which is formed by these three pieces here. And these three pieces are exactly E1 complement times E2 complement. Okay? So I leave it to you to check that indeed the complement of E1 times E2, it's given by the union of these three sets. and these three sets are clearly disjoint. Well, since this one, it's disjoint to that one because the first coordinate here belongs to E1, here it belongs to E1 complement, and you can check that they are indeed disjoint. And this shows that, indeed, the complement of A can be written as a disjoint union of rectangles because F1 and F2 are sigma algebras, and therefore E2 complement belongs to F2, E1 complement belongs to F1, and E1 complement and E2 complement belongs to F1 and F2. So this proves that the second property of semi-algebra is satisfied, and therefore that the rectangles form a semi-algebra. So let me just make a remark about my picture. Assume that omega j is equal to r. So we have here r times r, and I represented E1 as an interval, E2 as an interval in my last picture. Well, in fact, the sets, the rectangles, are much more complicated because I'm allowing E to belong to E1 to belong to the sigma algebra F1. Okay, so F1 in the case of the line could be the Borel sigma algebra or the Lebesgue sigma algebra, and therefore the set E, which I'm taking here, it's not an interval, but would be any Borel measurable set or any Lebesgue measurable set. So the rectangles are form a much richer class than what we usually call a rectangle in everyday life. So the product of an interval with an interval, right? So the rectangles here are much richer, right? I'm allowing the set E1 to be any Lebesgue measurable set, the set E2 to be any Lebesgue measurable set. So this picture is completely wrong, or at least does not represent what a typical rectangle is in the terminology I just introduced. This is just a simple remark. And now, what did I show? I showed that the sets F1 times F2 forms a semi-algebra. Okay. Now, I will define two objects. The first one is the sigma algebra generated by the rectangles. So I will represent by F1 star F2, and I will denote that by F simply. This will be the sigma algebra generated by the rectangles, which we usually represent as sigma of F1 times F2. Okay? So this is the smallest sigma algebra which contains the rectangles. And Carré-Theodori theorem will allow us to extend a measure defined in the rectangles to a measure defined in F in a unique way if the measure defined on the semi-algebra is sigma finite. So now I will define a function in the semi-algebra, and then I will prove that the function I defined is sigma additive and therefore is a measure. So I want to define mu in F1 times F2, taking values in R plus, extended. And, well, as I said, take a set which is a rectangle. So this set will be written as E1 times E2, where E1 belongs to F1 and E2 belongs to F2. So what is the natural definition of mu of E1, E2? Well, it will be mu1 E1 times mu2 E2. Right? Again, we have, these are non-negative numbers, so it's well defined, provided we convey of what is 0 times infinity, and again we are using that 0 times infinity it's equal to 0. So if mu2 of E2 is equal to plus infinity, mu1 E1 is equal to 0, we are setting mu of E1 times E2 as 0. So this is the definition of a rectangle. And now, if we want to apply Carat-Theodori, we have to show that this function is sigma additive on the rectangles. So this is my next claim. So proposition. Well, I'll first show that mu is additive. And to show that mu is additive, I will need a lemma, which will be used many, many times here, which can be stated as follows. Take an element of the product sigma algebra. So A, it's an element of F1 star F2, which I'm representing by F, remember. Okay, so this is the smallest sigma algebra which contains the rectangles. Now, for any subset A of omega, I can define what I will call the section at x of A. So I'm fixing x in omega 1, and I want to define the section at x of A, or I can also take y in omega 2 and define the section of A at y. So let me draw a picture before I define. So let's say that here it's omega 1, then I have here omega 2, and there is here some set, which is A. So the section AX for a fixed x in omega 1, so I'm fixing x in omega 1, and what I'm doing is I'm finding all y's such that xy belongs to A. So here's AX, right? So I'm fixing x and I'm finding all points y in omega 2 such that the pair xy belongs to A, which is here in my example this set. And similarly, well, notice that if I take here x equal to here, the AX will be just the empty set. For that x, it will be this interval. And I'm doing now the same thing for y. So I'm fixing a point y in omega 2, and I'm finding all points x such that xy belongs to A. So if y is this point, AY will be this interval. If y is this point, AY will be the empty set. So this is the picture. So now let's write what I just said. So AX will be all points in omega 2 such that xy belongs to omega, to A. So to the set A, which is fixed. And so I'm defining the section for any subset of omega, not only for the elements of the sigma algebra F, but for any subset of omega. Of course, if A belongs to the sigma algebra, these sections will have special properties. So AY will be defined in a similar way. I'm taking all points x in omega 1 such that xy belongs to A. And what I want to observe is that AX, so x it's a point in omega 1, AX it's a subset of omega 2. And similarly, y for y in omega 2, AY, the section at y of A, it's a subset of omega 1. And the lemma I want to state reads as follows. Well, if you take any set A in the sigma algebra F, then, and let me erase the picture to state the lemma, then for all x in omega 1, Ax belongs to F2. So remember, Ax, it's a subset of omega 2. So I'm saying that if the set A is in the sigma algebra, the product sigma algebra, then for any x, its section at x belongs to the sigma algebra F2. And similarly, for any y in omega 2, the section of A at y, which is a subset of omega 1, belongs to F1. So we will use, I will prove this lemma, and we will use this lemma in order to show that mu is additive. So here's the lemma we want to prove. The proof is very simple, and the technique I will use in this proof, it's very important. We used it already at least once, and we certainly will use it many more times. So I want to show that a certain property holds for any set in a sigma algebra. So how should I proceed? Well, I will define by C, say, the class of sets which fulfill this property. I will show that this class contains the rectangle, that it is a sigma algebra, and therefore that it contains the smallest sigma algebra which contains the rectangles, which is the product sigma algebra. So let me call this property alpha. So I will prove alpha. So let me call C all sets A in the product sigma algebra such that A fulfills alpha, which means that for any x in omega 1, Ax belongs to F2. So this is the definition of the set C. So now I will prove two properties. I first will show that C contains the rectangles. So that C contains the class of rectangles. So in order to do that, let's take a set A in F1 times F2. So A is a rectangle. So A can be written as E1 times E2, where E1 belongs to F1 and E2 belongs to F2. And now let's see what is the cross-section. So let's show that A fulfill property alpha. So let's fix x in omega 1. Let me draw here a picture of a rectangle. So here is the set E1. Here is the set E2. So the rectangle will be just this rectangle. And now I'm fixing a point x in omega 1, which is here, and omega 2 here. So you see, either I take a point outside E1, in which case the cross-section will be the empty set, or I take a point x in E1, in which case the cross-section is equal to E2. So what I claim, and I leave it to you to check rigorously, is that Ax, it's either the set E2, and this is the case when x belongs to E1, or it is the empty set if x belongs to E1 complement. Well, since E2 belongs to F2, and the empty set also belongs to F2, because F2 is a sigma algebra, we see that whatever x, the value of x is, AX always belongs to F2, because it's either the empty set or the set E2, which is an element of F2. So this proves that A indeed belongs to C, and therefore that the rectangles are all contained in the set C. Okay, so let me erase this proof, and let's now prove a second claim. So my second claim is that C is a sigma algebra. And to show that C is a sigma algebra, I have to prove three properties of C. So let's prove these three properties. The first one is that the set omega belongs to C. So let's see that the set omega belongs to C. So in order to show that omega belongs to C, I have to fix a point x in omega 1 and show that the cross-section at x of omega belongs to F2. So let's fix a point x in omega 1. Let's consider the cross-section at x of omega. Well, but this is omega, it's the set omega 1 times omega 2. And we have seen in the proof of part A that the cross-section of a rectangle, it's either the set omega 2 or the empty set, but since x, it's of course in omega 1, the cross-section it's omega 2, and omega 2 it's an element of F2, because F2 it's a sigma algebra. Therefore, omega is certainly an element of C. Now let's prove the second property. The second property of a sigma algebra is that it's closed by complement. So let's take a set A in C, and I want to show that the complement of A belongs to C. So let me try to prove that in this space. So let's consider A in C. I want to show that A complement is in C, so I fix x in omega 1, and I have to consider the cross-section at x of A complement. And what I claim is that this is exactly the section at x of A complement. If I can prove this identity, well, I know that A by assumption belongs to C, therefore AX belongs to F2, and since F2 is a sigma algebra, it's closed by complement, and therefore this set belongs to F2, which proves property 2. So the only thing I have really to do is to show that this identity holds. Well, so let's recall what's the cross-section of a set. So these are all points y in omega 2 such that xy belongs to A complement. This is just the definition of the section at x of the set AC, the complement of A. So to say that xy belongs to the complement of A is the same thing as say xy does not belong to A. So these are all points omega 2, y in omega 2, such that xy does not belong to A. Well, but this is exactly, so if we remember what is A, the cross-section, so let me write that here, the cross-section of at x of A, these are all points omega in omega 2 such that xy belongs to A. So you see that this set, it's exactly the complement of this set, right? If you have a point here in this set, this means that xy does not belong to A, and therefore y does not belong to this set. While if you have a point in this set, then xy belongs to A, and therefore y does not belong to this set. So this set, it's exactly the section at x of the set A, complement, and therefore we have exactly proved this identity. So up to this point we proved that omega belongs to C and that C is closed by complements. So now it remains to show the third property of sigma algebras is that assume that you have a family AJ in C, we have to show that the union of AJ belongs to C. So let me erase that, write it here. And let's prove the third property. So I'm starting with a family of sets in C. And I want to show that the union of AJ belongs to C. So to show that the union belongs to C, let's fix a point x in omega 1. And let's consider the union AJ. And let's take the section at x of this set. So these are all points, by definition of this section at x, these are all points y in omega 2, such that xy belongs to the union of AJ. And what I claim is that this is exactly the union of y in omega 2 such that xy belongs to AJ. So let's check if this identity holds. So assume that you have a point y in this set. If y belongs to this set, this means that xy belongs to this union. If xy belongs to this union, means that xy belongs to AJ for some j. And therefore, that y belongs to this set for that j, and therefore it belongs to this union. So this proves that this set is contained in that one. So now assume that you have a point in this union. If you have a point y in this union, it means that it belongs to one of these sets. If y belongs to one of these sets, this means that xy belongs to that aj. If xy belongs to that aj, of course xy belongs to the union of aj, and therefore y belongs to that set. So this proves the other inequality. So these two sets are equal, but what do we have here? Well, here we have exactly the section at x of the set aj. So this is exactly equal to the section at x of aj. So we proved this identity. Well, but we assumed at the beginning that the set aj belonged to C. If the set aj belongs to C, this means that the section at x of aj belongs to F2. So for each j, this set here is a set in F2, and therefore the union, because F2 is a sigma algebra, belongs to F2. So this set belongs to F2, which means that the union of aj is in C, because its section at x, it's an element of F2. And this proves, therefore, our claim B, that C is a sigma algebra. now we can conclude. Well, on the one hand, C contains the rectangle. On the other hand, C is a sigma algebra. Therefore, C must contain the sigma algebra generated by the rectangles. Right? Because the sigma algebra generated by the rectangle is the smallest sigma algebra which contains the rectangles, and this is exactly our product sigma algebra, which I'm representing by F or by F1 star F2. This means, of course, the way in which I define C is also contained in F1 star F2, therefore C is in fact equal to F. But what we proved is that any element of A is in C, element of F is in C, and therefore if I take any set A in the product sigma algebra, it has to satisfy this property. And we can prove the second property exactly in the same way. So you see, here we are again using this strategy in order to prove that a certain property holds for any set of a sigma algebra. Right? We are defining C as the family of sets which satisfies this property, and we are proving that this set is a sigma algebra and that it contains a class of sets which generates the sigma algebra. And this strategy, this method of proof, it's extremely important and will be used many, many times. So now let's prove that mu is additive. What does that mean? It's additive in the rectangles. So this means that if I take A and AJ for j between 1 and n in F1 times F2, and if A can be written as the sum of AJ, I have to prove that mu of A is equal to the sum of mu of AJ. This is additivity. Right, so I'm representing a rectangle as the joint union of rectangles, and I want to show that the measure of this rectangle is equal to the sum of the measures of the smaller rectangles. So if you want a picture, so here is a rectangle. So let's say that here again I'm working with omega 1 and omega 2, and here it's a set E1, here is a set E2, and I'm representing this rectangle as the union of the joint rectangles. So here's an example. I represented E1 times E2 as the union of all these rectangles, and what I want to show is that the measure of E1 times E2 it's equal to the sum of the measures of these smaller rectangles. Well, what are we going to use? A, it's a rectangle, so A can be written as E times F. And we have seen that if I take the section at x of A, what I get is that this section, it's either the empty set if X does not belong to E, or it's F if X belongs to E, to F. So, and this holds for any rectangle, right? So if I have a set which is a rectangle E times F, AX will be either F or the empty set, F if X belongs to E, and an empty set if X does not belong to E. So, on the other hand, we also have seen that if I take, in the previous lemma, we proved that if I take A, which is the union of some sets AJ, I take the section at X. So this is the section at X of this union. And we have seen that if I take a union of sets and I take the section is the union of the sections. Well, now I'm writing in this way because I'm not sure if these sections are still disjoint. Well, at least I have to prove that. What we proved before is that if I take a section of a union, even if it's countable, then this section of this union is the union of these sections. So here I have AJ, and I'm taking the section at X of AJ. So my first observation is that, in fact, this union, it's a disjoint union. So I want to replace the union by this sum, and that I have to prove. So I have to prove that AJX intersection AKX, it's empty. But what is the first set? The first set is all points y in omega 2 such that xy belongs to AJ. And the second set are all points y, let's say y prime in omega 2 such that xy prime belongs to AK. And I claim that these two sets do not have any intersection, because if they do have, if I have a point y which belongs to both of these sets, this would mean that for that precise x, xy would be in AJ and xy would be in AK. So AJ and AK would have a non-empty intersection, but AJ are disjoint sets. So these two sets have no intersection, and therefore these sections are all disjoint 2 by 2. So this, I just proved that this intersection is empty if J is different from K, and therefore I can replace here the union by the disjoint union. So now let's go back to our formulation. So I wrote A as E times F. Now I will write AJ as EJ times Fj. And I have a similar formula for the cross-section at X. The cross-section at X of AJ, it's either Fj if, so let me write that. So what I'm here, let me just add J here, so that to represent this set AJ. So that will be Fj if X belongs to AJ, and it will be the empty set if x does not belong to aj. So let me use that here. This means that ajx, I'm taking here a union. So if I take the union of the empty set, I can just ignore, and I can make this union only over the sets fj. These sets fj, but which sets fj? Well, all those for which x belongs to aj. So I can represent that as, well, here I'm taking the indicator of aj and I'm computing that at the point x. So remember, this is the indicator of the set aj. So it takes value 1 or 0, 1 if the point belongs to ej, 0 if it doesn't. So this expression, it's equal to 1 if x belongs to ej, and it's 0 if x does not belong. Another way in saying that is that I'm summing here, x is fixed, so I'm not summing over all j's, but I'm summing only over all j's for which x is in ej. Which means that I fixed x, and I'm representing ax. Ax, remember, it's equal to f. So let me assume that x belongs to E. If x belongs to E, this set it's f. So if x belongs to E, this set is f. And what I'm saying here is that f, it's in fact equal to the union over all fj's. But which fj's? Well, all fj's for which x belongs to ej. So let me go to our picture here to say what we are doing. Well, what we are doing is that we are fixing x in E. And what we are saying is that if now I take the cross-section at x, well, we know that the cross-section of this set at x, it's the set f. And we are representing this set f as the union of, in this case, 4 sets, which are these 4. Of course, if the value of x change, so if I take here another value of x, now I'm representing the same set f as the union of all these now 3 sets, if I'm taking here. Right. As the union of that one with that one with that one. So we have different representations of the set f as the union of the sets fj. These representations depend all on the set x. But what's important is that, well, f, it's a subset of omega 2, so it's an element of f2 as well as the fj. So I can write that mu2 of f, because mu2 it's a measure, so it's additive, and since f it's equal to these fj's, mu2 of f it's equal to the sum of mu2 of fj. But I'm not summing here over all j's, only over those j's for which x is an element of ej. So we have this representation provided x belongs to E. And so while if x does not belong to E, what we have is that here Ax is the empty set. Here, since all these sets Ej are contained in E, we have here only empty sets. And so we have a trivial identity that the empty set is equal to the union of some empty sets. So I'm allowed here to add the indicator of E. Right, so we just proved this identity. If x belongs to E, then we have mu2 of f, which is equal to the sum of mu2 of fj, but over all j's for which x is in ej. So this is a way at which you can read this formula. Another way at which you can read this formula is the following. Well, what do I have here? On the left-hand side, I have a simple function. This is the indicator of a set in F1 times a constant. And on the right-hand side, I also have a simple functions, since it's a finite sum of indicators of sets which belong to F1 times constants. Since these two simple functions are equal, I can just take their integral on both sides. And if I take the integral with respect to mu1, what do I get? Well, the integral of a simple functions is just mu1 times mu1 of e times mu2 of f, but this is exactly mu of a, because a is e times f, and we have defined mu of a as mu1 e mu2 of f, and this is exactly what we get here. And on the right-hand side, we have by linearity a sum, and what do we have here? Again, mu1 of ej times mu2 of ej, but since aj is ej times fj, this is just mu of aj. So we have that mu of a, it's equal to the sum of mu of aj, which is exactly what we claimed. So this is the proof of the additivity of mu, and the sigma additivity, it's exactly proved in the same way, where instead of having a finite number of sets aj, we have a countable number of sets aj, and the only thing we used, it's here, that the fact that I'm taking a countable union in the section, but we have seen in the proof of the lemma, so that even in the case of a countable union, I can exchange sections and unions. The same argument will show that these sets, these sections are all disjoint. So we will have this representation with now an infinite sum instead. So we can apply the same argument, and here we have an infinite sum instead of finite sum, so we cannot apply again the linearity, but what we will use instead is the monotone convergence theorem, saying that this infinite sum is in fact a limit of finite sums, and by the monotone convergence theorem we can exchange the limit with the integral, and therefore we will get that we can exchange the infinite sum with the integral. So the same argument shows in fact that mu is sigma additive. And so this completes the proof of the fact that the function mu that we defined on the rectangles, on the semi-algebra of the rectangles, is sigma additive, and therefore that the first step in order to use Theodorus theorem is in force. So let me summarize what we did up to this point. We defined f1, f2 times f2 as the family of rectangles, and we proved that this family of rectangles is in fact a semi-algebra. Then we defined a function mu on f1 times f2 in R plus extended as if you take mu of e times f, then this is mu1 times e, mu2 times f. So we defined mu in the rectangles in this way, and we proved that mu is sigma additive. Now I want to use Theorem, so let's assume that mu1 and mu2 are sigma finite. This means that I can write omega 1 as a union of Ej and omega 2 as a union of Fj, and such that mu1 of Ej, it's finite, and mu2 of Fj, it's finite. Right, so I'm assuming that mu1 and mu2 are sigma finite, and so what I claim is that omega, which is omega 1 times omega 2, it's equal to the union of Ej times Fj. Right, you can check if you take a point, well, of course, Ej and Fj, it's contained in omega, and therefore the union is contained in omega. On the other hand, if you take a point x, y, a pair x, y in omega, well, x will belong to omega and therefore will belong to one of these Ej. I'm assuming here that Ej forms an increasing sequence. You can always assume that without loss of generality, and that Fj, it's also an increasing sequence. So you take a point x in omega 1, so it belongs to this union, which means that it belongs to some Ej. If it belongs to that Ej, it will belong to all Ek for k larger than j. Same thing for y, and this means that xy will belong to some Ej times Fj for a sufficiently large Ej, and therefore that xy will belong to this union, which proves that we have this identity. And therefore, we are writing omega as a countable union of rectangles, and the measure of these rectangles, Ej times Fj, by definition, it's mu1 Ej times mu2 Fj, which is finite because mu1 of Ek for any k it's finite, and mu2 of Fk it's finite for any k. Therefore, this is finite. And this proves that omega, it's in fact sigma finite for the measure mu. Since it's sigma finite for the measure mu, and mu it's sigma additive on the semi-algebra, we can extend, by using Theorem theorem, mu to the sigma algebra generated by the rectangles, which is exactly the product sigma algebra, which we are representing by F1 star F2. So this concludes the extension, the definition of this measure mu in the sigma algebra generated by the rectangles.